All right, this is problem number 6 from chapter 8 in your textbook. It has a figure associated with it, so I'm going to sketch that out really quick. It looks something like this, where there's an object, a mass, that is fixed here at some point P, I think they call it, that is a height h above the ground, like so, and then it goes into this loop, which has a radius. This is kind of a circular loop, so it tells you that the radius here is equal to r. And then later, there's also a picture with the object here at this point, which is a distance r above the lowest point. So that's kind of the picture. That's not the world's best, but that's pretty close to what they have sketched out there. And the problem describes that a mass, it has a certain mass, describes what that is, 0.032 kilograms, can slide along the frictionless loop, the loop, with a loop radius of 12 centimeters, so this r is equal to 12 centimeters. The block is released from rest at point P at a height of 5.0 times r. So it tells us that the height here is equal to the quantity 5.0 times the radius r, which is nice. It doesn't tell us, so the actual, I mean, we could figure out what that is, right? R is just 12 centimeters, so we could figure that out. That's not a problem. How much work does the gravitational force do on the block as the block travels from point P to, part A says to point Q, and so how much work does gravity do on this, right? So the work done by gravity is going to be equal to, we can do this from lots of ways. We know that that force is constant, and so I think we can write this down as the force of gravity, the work done by the force of gravity is equal to the scalar product of the gravitational force with the displacement that happens to be in the y direction, right? Or we could actually write something like this, delta L, like the most generic way of describing this. And that's, we can write this because the gravitational force is constant. Oops, force. Because that's a constant value. So we can write this expression of the scalar product of the force and the displacement, delta L. Right, there's a nice little scalar product here. It turns out that because of the fact that we can look at the actual multiplication of this, we can say something, one way to solve it would say that the magnitude of the gravitational force times the magnitude of the displacement times the angle between the two values, or times cosine of the angle between these two vectors is equal to the work done. Right? So we can look at what the direction of the force is. So our gravitational force that acts on this object is always vertically downward. And the displacement in this case also happens to be downward. So this is in general, the general displacement. But if we want to look at the magnitude of that particular displacement, we can do a couple of things, right? We can consider the fact that here's theta, and well, we need to know the displacement. The displacement would actually be this magnitude right here, right? That's how far it actually travels. That would be delta L, which we don't exactly know how far to the right this moves. So that seems problematic. So actually this expression for the scalar product doesn't seem like it works very well for us. But what we can do is use some, I mean, for many of you this may seem almost second nature. I hope this becomes more comfortable as time goes on. But what this is really asking us for is the scalar product of these two things. Another way to write that out would be to say that we want to take the vector quantity of the gravitational force, which is the weight, mg, and its direction, which happens to be minus j hat. We'll call positive j hat. Vertically upward, we'll call that positive j hat. So it's that quantity, the scalar product of that quantity with the displacement, which is going to have some displacement in the x direction, I hat, plus some displacement in the y direction, j hat. Okay? So it is the scalar product of these two quantities, because this moves some value in the x direction, and it moves some value in the y direction. All right? And if we wanted to be if we called positive up, this should really be, well, we can talk about whether this quantity delta y would be negative or not, or whether the j hat. So for now, let's leave this as j hat being positive and recognize that our delta y in this case is going to be a negative quantity because it's going opposite of that direction. Here, it doesn't matter, in this case, it doesn't matter what the displacement in x is because we're taking the scalar product of this displacement in x with this quantity in the gravitational force. And so j hat, the scalar product of j hat or minus j hat and I hat gives us 0. And so that term kind of goes away. The only term that we pick up is that in the y direction. So that's why the work done by the gravitational force is equal to mg times the displacement delta y in the j hat direction, right? We actually pick up a minus sign from this particular term, and also recognizing that this delta y is going to be negative. So we could account for that by calling this, we could draw a little absolute value here into the delta y and make sure that we only account for the negative sign one time by putting the negative sign here on j hat, knowing that it goes in the negative j hat direction. So we take the scalar product of that. We know that the work done by the gravitational force is going to be some positive quantity, which hopefully looks familiar from some of the questions that we've done in class. So that's the answer to part 1, or part A rather. And then part B is what is the gravitational force, what is the work does the gravitational force do on the block as the block travels from P to the top of the loop? Oh, sorry, technically I didn't answer this question completely. So, well, if the height starts off as 5.0 times r, and then it finishes up with a height of just r, then the change in y here is going to be equal to mg. Delta y for that scenario is 4.0 times whatever the r is, right? We're simply taking the final position, r, minus the initial position, which was 5.0 r. And remember, we already took care of the negative sign, so we'll call this the absolute value. Leaves us with 4.0 r. So that's question A. Question B would simply take in this exact same expression. The work done by the gravitational force is equal to the object's weight times the displacement to go to the top of the circle, which going to the top of the circle is going to be 2r minus 5.0 r, right? Just two values of that, the radius of that loop. So that's, taking the absolute value of that would leave us with 3.0 times r, right? So it's going to do less work, there's less work done by gravity as it goes to the top. You could also, if you wanted to, break this into parts and look at the work that the work done by the gravitational force as it goes from its highest point to its lowest point, and then again look at the work done by the gravitational force as it goes from its lowest point to its highest point. That would be fine. I mean, you would be able to find out exactly what this is. What you would do is you'd get, essentially that would be taking mg times 5r minus mg times r, right? So you'd be taking those into different pieces, and that's fine if you feel more comfortable doing that. But we can do it all at once because we know the total displacement is going to be 4.0 times the radius in case 1 and 3.0 times the radius in case 2. Not without having to worry about exactly the distance it covers, exactly how it gets from the beginning to end point. So we're going to go on to the other parts of this problem in the next clip.